Okay, so from now on, I want to give several videos on limit theory. So basically, we will first start with the limits of functions. We can also define limit of sequences, but basically all the syllabus in NA goes, we first talk about the limits of functions, and then maybe after several chapters or several videos on YouTube, we can talk about the limit of a sequence. So first thing we need to be aware of is the definition of interval. So one might ask, why should we care about the interval? So this will be very important later, because we use interval to denote the concept of close enough for a point. So let's look at, for example, just one point x in the real line. And then what are the points that have distance 1 to this point? So these are exactly 2 points. So one of them is x plus 1 and the other is x minus 1, right? These two are the points whose distance to x is equal to 1. And then in general, the distance of A to B, or distance from A to B, is equal to not anything else but the absolute value of A minus B, right? Because you can think of this as the geometric meaning of the absolute value of a difference, right? So if you have 2 points, let's say A and B, so sometimes A can be bigger, B can be smaller, but if you consider this distance, it has to be non-negative, right? It cannot be negative. It cannot be a negative value. So then you have to take the absolute value of the difference. So if you want to find some point whose distance to x is exactly 1, then this means y minus x, if you take the absolute value, it is equal to 1. So this means this absolute value is either plus or minus 1. So then this value is, if you add x to both sides, then y is either x plus 1 or x minus 1. Okay, so this is the simplest case, but usually we care about the points that are close enough to x. What does close enough mean? It means, for example, it is close that for all x that has distance at most 1 or less than 1. So that they correspond to the closed intervals around x and then open intervals around x. Okay? They are special because the middle point or the midpoint is exactly at x. So it's very special. So what is the closed interval? X minus, we'll call it a, okay? X minus a and then x plus a. This is exactly all the points y in the real numbers, such that the distance from y to x, or the absolute value of y minus x, is less than or equal to a, right? Because, for example, when it's equal to a, then it's exactly x plus a and x minus a. And when it's, for example, 1/2 of a, or a over 2, then it's exactly x plus a over 2 and x minus a over 2. And then when this absolute value is minimal, so then this is 0, then it means we're taking exactly at this point. So when the absolute value goes from the biggest, which is a, to the smallest, which is 0, we actually go from this pair to this pair and all the way to x. So then if we consider all the sets, if we consider the set of all the points, then it is the closed interval. Okay? So which means we have shown that y is in the closed interval if and only if the absolute value of y to x, the absolute value of y minus x, or the distance from y to x, is at most a. Okay? And similarly, we can have the notion of an open interval around x. Okay? When I say around, it means it is symmetric along the point x. Okay? So then it will be x minus a and x plus a. So this will be the set of all y in R such that the absolute value is less than a. So which means y is in the open interval x minus a, x plus a if and only if this absolute value is strictly less than a. And sometimes we are interested in the, let's say, the deleted interval, or it's also called deleted neighborhood. So let's just, for now, we will call it a deleted interval. So it can be either we delete from a closed interval or from open interval, but in most cases we delete the point from, we delete the x itself from the open interval, okay? So you can call it the deleted open interval. So it is nothing else but the set of all x whose distance to x is bigger than 0 and less than a. So we know that this absolute value is equal to 0 if and only if y is the point x itself. So if we ask that this is bigger than 0, then we get the deleted open interval, which is exactly the interval excluded, the interval excluding this point. So this is this is x minus a to x union x to x plus a. Or if you wish, it is the interval from x minus a to x plus a, and then deleted the point x itself. So this is exactly the set of all real numbers y, such that the absolute value of y minus x, or the distance from y to x, is bigger than 0 and less than a. So when we say this is bigger than 0, this is always bigger than or equal to 0, and this is 0 if and only if y is equal to x, right? The distance between 2 points is 0 if and only if it's the same point. So this is bigger than 0 just means we cannot take y to be x itself, right? So then we're taking all the points from x minus a to x, and then skip the point at x, and then go from x to x plus a. Okay, so this is the deleted open interval around x. We can also call it a deleted neighborhood. Okay? Neighborhood. Okay, so that's about the absolute value. So basically you have to be very familiar with this idea because it will happen many times. And whenever we say a point is close enough to a point, we mean for some very small a, and then for all the y that are in the either open interval or closed interval or deleted open interval, depending on the context. Now, let's talk about the limit. So if we are given a function f, so it's a function. Usually in the calculus, we are interested in the functions from R to R, and so if f is a function from R to R, then this is called the domain, which means it is the set that are it is a set of all the numbers that f is defined, okay? And then whenever it's defined, we are assigned a value to it. So for example, for each x in the domain, in this case it's R, but it can be anything. For example, in this course, it can be anything, let's say any a, which is a subset of R. Okay, so we can define functions on only subsets of R. So if x is in the domain, let's say x is in A, then we have to assign to x a value, let's call it f of x. So it has to be in this codomain R. So a codomain is some big set that contains all the values, right? All the f of x are called the values of the functions, of this particular function. And for each a real valued function, we can sketch a graph. So let's say in the simplest case, if f is from R to R, then we can sketch a graph like this. We can assign to each x a value, let's say x comma f of x. So this point means that the value at x is f of x, so we denote this here. Okay, so so then we'll have a graph. Sometimes it to be so for now, let's assume it is continuous, like it is just continuous as we want. But sometimes it doesn't need to be continuous at all. It actually doesn't need to be continuous at any point. Okay, but for example, let's just this example. So at this point, so all the way to this point, it is like in this graph, and then at this point, it is equal to 0, and then from this point to the right, it becomes this graph. Okay, so then you can see it is not continuous at this point. And then we don't really need to define the value at this point at all, because when we talk about limit, we're only talking about the tendency as x approaches to this value. So now let's take a look at this function. So at this point, we will denote it. We'll call the value to be 1, and then when it's bigger than 0, we'll call it just equal to x, and then when it's less than 0, I will call it's equal to x squared. Okay, so which means for this graph, if f of x is equal to x if x is bigger than 0, and it's 0, it's 1 if x is equal to 0, and then it's x squared if x is less than 0. So the point is that if you exclude this point at all, and then you consider all the points as x goes from right to 0 or from left to 0, right? You just don't care about this point at all. Then what you notice is that all the y values or all the heights of this graph, it approaches to 0, right? Because at this point the height is that, and it becomes smaller, and then in the end you can see that it tends to 0. It happens the same on the right. It also tends to 0. So you can see the value at this point doesn't really matter. And an interesting thing is that we don't really need to define a value at this point. We can totally exclude this point. We don't need to define the value at this point at all. But we can still define its limit, and then we still want this limit to be 0, because no matter we go from left or right to 0, you can see the y value both approaches 0. Both approaches 0. So we want to have a notion of limit without the definition, without the value at this point at all. But how can we define it? So what we want is actually a definition that basically means if x is small enough, if x is close enough to this point, so in this case it's 0, but actually it can be any point. So in general, what it means to be, what it means for a function to have a limit at a point, it means, so at this point we don't care about its value at all, but we want, you can see both sides to approach this same value. Let's call this value L, okay? Because L is used to mean the limit. L is used to mean the limit, so we call it L. And this function, let's call it y equals, so let's call this function f of x. Okay, so in the graph, it should be y equals f of x, but this function is called f, or f of x. And let's say this point is a. So we want to define what it means for the limit as x approaches a of f of x to be L. So this means as x approaches a, f of x approaches L. And we usually denote this by f of x approaches L when x approaches a. Okay? So if you are familiar with this enough, then you can just denote by this. Okay? So which means the point, the point here is that it tends to this point L. Okay? So you can see, for example, in this case, it doesn't need to be equal to L at all, but it's still true that it will converge to this value, or it will tend to this value. So we want to have a correct definition of what it means to be convergent to a point. But how will we define it? So here we want, this is the trick, or this is the hint. We want for all close enough x, we will have f of x is close enough to L. Which means if we look at all the points that are close enough to L, let's say if we look at all the points that has at most, let's say 0.1 or less than 0.1 distance to the point to the value L, and then we look at all the x such that f of x is within this interval. Okay, so now in this example, so let's say we're looking at L minus 0.1 and L plus 0.1. Then all the intersection we have here, actually we have 2 parts, right? So for exactly for these x, right? For these x, so if we project them to the x-axis, then you will see that these are exactly the points, and we don't have this point defined, right? We don't need this point to be defined. So this is actually open, or like it's deleted here. So you can see that for all the x that is colored in blue on the x-axis, it's exactly those points whose value, or f of x, are within L minus 0.1 and L plus 0.1. And you don't really care, when you talk about limit, you only care about the points that are close enough to A, which means you don't need to care about this at all. Why? Because here, this is not connected, right? These 2 intervals are not connected. And you want all close enough points to have values within this interval L minus 0.1 to L plus 0.1, which means all you care is this interval, and it doesn't. Usually it is not symmetric, right? But all you need is some symmetric. So let me just make it not symmetric. So let's say, for example, here on the right, it's very big. It's a very big interval, but on the left, it's very small. So all we need is that we can find some open interval centered at A that is small enough. Okay, that when we mapped on the graph, it is entirely within this interval. Okay, it has to be contained in the set L minus 0.1 to L plus 0.1, but it doesn't need to be the same. Okay, it has to be small but not big. So this is actually the definition. It is a correct definition of a limit, at least for 0.1. Okay, so if we want this f of x to approach L when x approaches A, then at least for this 0.1, we have to find some, let's call it delta, some delta bigger than 0, such that for all the values x close enough to A, how close? We want the distance to be less than delta, okay, and bigger than 0, because we don't have this point. So for all the points x within this A minus delta to A union A and A plus delta, we want this to have, so we want to imply that f of x must be within the interval of L minus 0.1 and L plus 0.1. Does that make sense? So this is a necessary condition, but it's not sufficient, because this is only for 0.1. If we want it to be close, it can be arbitrary close, which means this is true for any small enough epsilon, or small enough, we can call this 0.1 epsilon. And here, this is a special case when epsilon equals 0.1. So we want this to be true for any epsilon, okay? And definitely this delta is, you just need to find one value of delta. Does that make sense? This is clearly false if this delta is very large, right? Then you clearly have values that are beyond this interval. So all you need to find is some delta. So logically speaking, we want to find some delta bigger than 0, such that for all x in this interval we have that. Or we can say for all x in R, if x is in this interval, then this should be true. Okay? So which means we want to find some delta bigger than 0. But then you can see there is nothing special about 0.1. You can also have 0.01, 0.001, or any arbitrarily small real number, arbitrarily small. So you cannot have a criterion without using for all statement, right? So even if you have shown that this is true when this 0.1 is changed into 0.00001, but it still can happen that it does not converge because, for example, in this case, so if the graph is, so let's say this is L plus 0.001, this is L minus 0.001, and this is L, and then if you just zoom in a lot, then for example, if the graph here is just like it goes to, for example, L minus 0.000001 and then L plus 0.00001 like this, and then you can see clearly that this will converge to a value that is smaller than that, and this will be converged to a value that is bigger than that. So this is not convergent. So the problem is that you only prove it for 0.001, but what about smaller numbers? So this means this is not enough for 0.1 or any single number. It has to be true for all epsilon bigger than 0. That is small enough. Okay? So which means the correct definition of the limit of x goes to a of f of x is equal to L is that for all epsilon bigger than 0. We use this epsilon to denote the distance from f of x to L. Okay? We use this, it's actually not the distance, but we use it to describe the distance or to bound the distance. We use it to bound the distance from f of x to L, and we can find some delta bigger than 0. So this delta is actually, we use it to find some interval centered at A that has values close enough to L that I can say whose values are in the set L minus epsilon and L plus epsilon. Okay? So then for all x in the real numbers, so whenever x is in this small enough interval, let's say from A minus delta to A union A to A plus delta, we want to have that f of x is in the interval of L minus epsilon to L plus epsilon. So this should make sense, right? So this means, geometrically speaking, we don't care about this point at all. Let's call this A and let's call this L. All we needed is that for all epsilon bigger than 0, it can be arbitrarily small. Okay. For all epsilon, we want to find some delta such that when the x value is from A minus delta to A plus delta excluding A, then all the values are very, very close to L, that is less than epsilon. Okay, all we need is a bound. So you can actually change this definition into a closed interval. It doesn't matter, okay, because it just means close enough. So you can prove that they're equivalent by applying the trick of either epsilon or epsilon plus 1 or epsilon over 2, things like that. You can prove that they're equivalent. So the point here is that it's close enough. Okay. But this is still too complicated. We want to simplify this. I mean, although this is correct. So first let me rewrite. Let me write again of this definition. It's because it's super important. So the limit as x goes to A of f of x is equal to L is true if and only if for all epsilon bigger than 0, we can find some delta bigger than 0. It can depend on epsilon, such that for all x in R, if x is in the interval A minus delta to A union A plus delta, then this will imply f of x is in the interval of L minus epsilon to L plus epsilon. And then this is too complicated, but we know that we can rewrite this as, so let me just rewrite the entire sentence. So we cannot change this for all and there exists, and for all x in R. But then we can change this into if, so this is equivalent to saying that x, the distance of x to a, or the absolute value of x minus a, is bigger than 0. I have to emphasize this, because we don't care about the point, the value at this point at all. The function doesn't need to have a value at the point a at all. So if you don't have this condition, it means at least you have to define the value at this point, but you don't need to define it, right? So you have to add this bigger than 0. If you don't add it, you're wrong. Okay, so this is very important. Then this and also less than delta, then this means the distance of f of x to L is less than epsilon. I mean, for here it can equal, it can be equal to 0, right? Because for example, if it's the constant function L, then clearly when it goes from the left or from the right, then it will converge to the constant. So maybe that will be the first example. Okay, so then we can use this definition to prove some results that are easy to prove. So first we want to show that the limit of a constant function, let's say it's always equal to c for any value at any point a, so in this case f of x is always c. We want to show that the limit of a constant function is equal to itself, or I mean just the constant, which is a real number, for all points. Okay, so let's prove it. So which means we want to show that for all epsilon bigger than 0, we want to find some delta bigger than 0, such that for all x in R, I don't really want to write this. So maybe I just want to write for all x. Okay. Whenever I didn't say for all x in some set, I mean for all x in R. Okay. I don't want to be I don't want to be that rigorous, because I have to move on and I have to save time, right? Because it's a crash course, as I said. And what we want to show is that if x is close enough, if this is bigger than 0 and less than delta, then we want to show that the value, which is c, minus the value at c, should be less than epsilon. I mean, right here, this is the f of x. But it's a constant function, so it's always c. So then you can see it is trivial, because this is 0. And 0 is less than any positive epsilon, which means this is always true. Which means whatever x is, this is true. Which means you can just take any delta. So for example, you can take delta to be 1. So you can just say let epsilon be any positive number, and then take delta to be any value. You can just really say it's any value, but it's very, very special here. So maybe it's better to just fix some delta. Let's say delta is 1. So then if you want to show this is true, then you should really say let x in R and then assume this is true. But for simplicity, you just assume that you just assume this is true, okay? Because we always assume that x is a real number, okay? Then you want to show this is true, but then clearly this is equal to 0, which is less than epsilon. So which means we didn't use this condition at all. I mean, this is the simplest condition, so it makes sense. So we have proved that the limit of a constant function c is equal to c itself. Yeah, so I have to emphasize that when I say itself, I'm not, it's not the function itself, but the constant itself. Because the constant function is a function, but the constant is a real number. So maybe I should emphasize that this is a real number. The limit, if it exists, then it has to be a constant. It has to be a real number, sorry. And definitely a constant, because every real number is a constant. Okay, and we'll show, I mean, the second most trivial example is the limit of a linear function. So let's say the limit at, so for example, if it's 3x plus 5, and then if we evaluate at x, when x approaches, let's say 2, then we should, because this is actually continuous, right? Because it's things like this. And then when it comes to 2, it should converge to the value at this point, right? So if that's true, then we say it is continuous at this point. I will come to this. I will come to continuous functions later. So we want this to be actually 6 plus 5, which is 11. Okay, we want this to be 11. So how we prove it? Well, we want to show that for all epsilon bigger than 0, we can find some delta bigger than 0, such that for all x, I don't really want to write this, but I have to. If this is bigger than 0, if x minus 2 is bigger than 0 and less than delta, then we want to show that the absolute value of f of x minus this limit must be less than epsilon. Okay, so usually we will start by solving this inequality as the scrap work. Okay, so this is only for scrap work. You cannot write this as part of the solution. So you'll write this on the scrap paper. So you want to solve for this inequality, and for any, you want to solve this inequality for any positive real number epsilon, right? So then if you are given a positive epsilon, then this is simply 3 times 3x minus 6, right? Because plus 5 minus 11 is minus 6. And then this becomes 3 times x minus 2, because 3x minus 6 is 3 times x minus 2. So all you want is this is less than epsilon. So this is clearly just 3 times the absolute value of x minus 2. So you can just rewrite this as 3 times the absolute value of x minus 2 to be less than epsilon. So this is true if and only if the absolute value of x minus 2 is less than epsilon over 3, okay? But here, you want to find some delta, so now you can choose this delta for any given epsilon, right? It can be dependent on the epsilon, and it has to be dependent on epsilon. So which means you want to find some delta that is very, very small, such that if this is bigger than 0 and less than delta, then now it's less than epsilon over 3. But how will you choose this delta? You just need to find any particular value. Why not just choose delta to be epsilon over 3 and you win? Because if this is true, then it means it is less than delta and bigger than 0, right? So both of them are true. So clearly the second one is true. So then this is true, right? You can just choose this delta to be epsilon over 3 so that it is true. So now this is just for scrap work. You don't need to erase that for now. You can just keep it on the scrap paper. So then you just write let epsilon be 0, and then you want to take some delta, very, very special. So in this case, we take delta to be epsilon over 3. So actually the reason is that because here we have 3, so then we have to divide by 3. So then after we multiply by 3, it becomes epsilon, right? If this delta is epsilon, then after we multiply by 3, we get 3 epsilon. But we want this answer to be epsilon, okay? So we take it to be this value, and because epsilon is positive, so this delta must also be positive. So then now we assume that x is close enough to 2, so then it's less than delta, but delta is epsilon over 3. So then we want to evaluate this f of x minus L, but then this becomes simply 3 times the absolute value of x minus 2. But here, this is less than epsilon over 3, because we choose delta to be epsilon over 3. So then this is going to be less than 3 times epsilon over 3, which is equal to epsilon, which is not a surprising fact, because we choose this delta by solving this inequality a priori, okay? So usually we just want to solve this inequality based on some facts, like a basic algebra, and then we use it to find this delta to conclude this proof. And you can see that in this example, in almost every example, this delta will depend on epsilon, or you can say it can depend on epsilon, and usually it has to be dependent on epsilon. So we want to choose this delta very, very small, okay? So keep that in mind. We want delta to be small, not big, because it makes sense, right? Epsilon is arbitrarily small, but it's positive. And then for each epsilon, this delta should be smaller, right? When epsilon is smaller, delta should also be smaller. Then it makes sense. Because like this interval, when you take a smaller epsilon, then you have a smaller interval, smaller open interval around x. So that makes sense. So this delta should also be smaller as epsilon becomes smaller, but still positive. Okay. So this is about the limit. And then I will talk quickly about some limit laws. So the first thing is that if you have two functions that has a limit at the same point a. So let's say if this is a and this is b. So this is given, okay? This is the condition. Then you consider the sum. Then the limit of the sum will exist, and this value is equal to. You can imagine what it is. So it will be the sum of the limits. You can prove it using epsilon delta proofs. So which is just proved by definition. For any epsilon, you can find some delta. And because I don't have enough time, so I will not talk about that. Maybe you can just check it from any other source, and I will just skip that part. And also this is true if you change this into minus, right? So f of x minus g of x will also have a limit, and this limit will also be the difference of the limit, okay? So the limit of the sum will be the sum of the limit, and then the limit of difference will be the difference of the limit if both limit exists, okay? If at least one of them does not exist, then you cannot say anything about that, okay? Then you cannot use the limit law. So whenever you want to use limit law, you have to make sure that both limits exist. And also we can talk about, so also if this is true, then okay, so this is the first result. Okay, the second result is that when you consider the product, then the limit of the product will also exist. Okay, and also how it will be dependent on the existence of both limits. Okay, so then this will be equal to the product of the limits. And again, you can prove it rigorously using epsilon delta proof, which means for any given epsilon, you choose some small enough delta such that this is true. But it will be technical, and we don't have time for that. And the third thing is that one might be interested in the quotient of them. But then in this case, if it will exist, then it should be the limit of f of x over the limit of g of x, right? So then it should be like a over b. I mean, I should really plug in the value. So this is a plus or minus b. So this is a times b, but it doesn't matter. So then this should be a over b. The point is that if this is true, then b has to be non-zero. It happens to be the case. So if you want to use the quotient rule, then you have an additional assumption. So if b is non-zero, then this is true. I mean, if b is 0, then this does not make sense at all, right? So you can only have this rule if b is non-zero. And luckily, whenever b is non-zero, this is true. And you can prove this rigorously, but I don't have time for that. Okay? So now, and also you have another rule, which is called the scalar multiplication. So if so let's say this is the part A, okay? So this is the and then let's talk about part B. So if the limit of a single function exists, so let's call this is A at a point A, and C is any given constant, any real number, then if you consider the multiple of f of x by C, which is C times f of x, which means you multiply C on each value to get the new value, then this should be C times A, or just C times the limit of this function. So the limit of the function, which is simply C times A. So what it means is that, so we usually call, if you multiply a constant to a function, we call it a scalar multiplication. We call it a scalar multiplication. So this means the limit of a scalar multiplication is the scalar multiplication of the limit. Okay, so also like commute in some sense, right? If you consider the scalar multiplication and then you consider the limit, And it's the same as you first consider the limit and then consider the scalar multiplication. So they commute in the sense. But then you also have to be sure that you have to have this condition. Okay? You have to have this condition. So a priori this limit must exist. Okay? Now, if you have all these limit laws, then what you can do is you can actually show easily that all polynomials are continuous. So we will not give the definition of a continuous function that early, but maybe we'll give a definition in the next video. So we just need to show that if p of x is a polynomial. So a polynomial is a function that can be written as a0 plus a1x plus a2x squared plus all the way up to an xn, where an is non-zero, and then all the coefficients a0 up to an are real numbers. Okay, any real numbers, and then this an is called the leading coefficient. If it is non-zero, it is called the leading coefficient. And then the corresponding n is called the degree of the polynomial, denoted by degree of p of x. It is called the degree of the polynomial. And then this a0 is called the constant term. Okay, so you can similarly call this a1 the term of the first order, like first order term, things like that. But most importantly is about the constant term and the highest term or the leading coefficient. Okay, but it doesn't matter here. This is just about the definition of concepts about the polynomials. But here, what we want to show is that for any a in R, which means for any point in the real numbers, the limit as x approaches a of p of x is actually equal to the value at this point. So later, basically just in the next video, we'll see this just means that every polynomial is continuous. This just means p is continuous. Okay, so this means this statement shows that every polynomial is continuous. So how do we show it? So first, we can mimic the proof. To make it even simpler, to prove that the limit of x exists. Okay, and so first we want to show a lemma, which is extremely easy to show. I will leave it as an exercise. So you can show that for any a in R, the limit when x approaches a of x is a. So this simply says that as x approaches a, x should approach a, right? So when x approaches a, x should approach a. This is trivial, right? But you have to prove it. So to prove it, how would you do? So let me quickly prove it. So you just let any epsilon bigger than 0. So you can just choose the same delta because here the coefficient is 1, right? It's only, you can only do that when it's linear, okay? But here it's linear. So you can just take delta to be epsilon itself. And then now if you assume that x is close enough to a, so if this absolute value is from 0 to delta, and delta is equal to epsilon, then you look at the distance from f of x, which is x in this case, and then the limit, which is a. So then this will be the same thing. This will be less than epsilon, and you win. Okay, so this basically shows that this is true for x, right? When p of x is equal to x. And then also you can show that we have already shown that the limit of any constant is equal to this constant. Okay? Now, we only need to use two limit laws, which are the limit law of the summation and also the product. Okay? We can call it sum rule and product rule. And we'll deduce that every polynomial is continuous. So First, let's look at the first term, a naught. If we look at the limit as x approaches a, then this is a constant. This is simply a naught. Okay. Now let's look at the first order term, what is a1x. The limit of a1x is, because by scalar multiplication, this is a1 times the limit of x approaches a of x. So this is a by the lemma. So this will converge to a1a, which is just you plug in the value x equals a, right? Then you get a1a. Now if you look at the second order term, which is a2x squared, then it is a2. So first it's a scalar multiplication, so it's a2 times the limit of x squared. But then x squared is x times x, so you can use the product rule. And you can use the product rule because this limit exists, right? Because it is a by the lemma again. So this is a2 times a squared. So then you can see just plug in x equals a again, which means you can do that on every term of the polynomial. So in the end, the limit as x approaches a of an xn is going to be an times the limit of x approaches a of x to the power of n. So then this is going to be an times a to the power of n. Now you can use the sum rule to add them up. So if you add them up, then it's the summation of x approaches the limit as x approaches a of p of x. So then this is going to be the limit as x approaches a of a naught plus a1x plus all the way up to an xn. So then by sum rule, I mean you can use it because all of these limit exists by these calculations. And then this is the limit as x approaches a of a1x all the way up to the limit as x approaches a of an xn. And then this is just by these computations, this is a naught plus a1a plus all the way up to a to the power of n. So then this is simply the polynomial evaluated at this point, because this p of x is equal to this for all x, and this is simply the value when you plug in x equals a. So this shows that p of x, when you evaluate the limit, you can simply plug in the value at this point. This means exactly that this function is continuous. And because this is an arbitrary polynomial, we have shown that every polynomial is actually continuous. Okay, so I think that's enough for this video.